Hello everyone, it's Mr. Fawcett and we are back for part 2 of our limits at infinity lesson. In part 1 we talked specifically about the end behavior, i.e. the limits at infinity of polynomial functions. Today we're going to get into the limits at infinity of rational functions, which are a bit more complicated, but if we think back to some concepts we learned in pre-calculus in Algebra 2, these should not be too difficult for us. So we're going to start off with this function right here. We have the limit as x approaches infinity and the limit as x approaches negative infinity of the following function. Now, with polynomials, we could just immediately look at the leading term, look at the exponent and the sign, and pretty easily figure out whether the function was going to positive infinity or negative infinity based on whether we were substituting in larger and larger positive numbers or larger and larger negative numbers. But rational functions are a bit different. Now, what's not different is that we still only need to pay attention to the initial the initial or the leading terms. So I'm going to rewrite the function, not the entire limit expression, just the function. Okay. And the nice thing is, when we are substituting in very large numbers, these leading terms are the only terms we need to look at, right? Because, well, it's pretty clear for the numerator, right? As x gets larger, the -4 plays less and less of a role, becomes far less significant. For the denominator, as we square our x, that's going to become more significant than just multiplying x by -9, as long as the numbers are large enough. So when the numbers are small and closer to 0, this is not the case, but as they become increasingly large, this function is approximately equal to this function right here, where we are only looking at the leading terms. So the red is approximately equal to the pink when x is very large. Okay, so if we took the limit of the pink function, that would be equal to the limit of our original function. But we can actually simplify our pink function more, and we can factor out the x to get 1 over x. And it's actually the easiest limit to take is the limit of this function right here. So first thing you can do when you see a rational function and you're trying to take a limit at infinity is focus on the leading terms and then simplify those if you can. Then, so this limit in black is going to be equal to the limit as x approaches infinity of 1 over x. Now, this should be pretty clear. As I divide 1 by larger and larger numbers, you could think about as I break a pizza up into more and more slices, the amount of size of each slice is going to get smaller and smaller and smaller. And if you had to cut a pizza up into 100,000 slices, each person would basically be getting nothing, right? They get a small sliver. So as you approach an infinite number of slices, the size of a slice is actually approaching 0, right? The area of each slice would be approaching 0. So the limit of this function is 0. Likewise, the limit of this function is equal to 0. So while these two functions, right, this function and this function are not exactly the same, the limits at infinity will be equal, okay? And one of them is easier to find than the other. Let's look at the limit as x approaches negative infinity. So same idea. I can rewrite the function, and I'm going to apply the same concept I did before. This function's approximately equal to x divided by x squared when x is very large. And again, I can simplify this to 1 over x. So the black limit is equal to the limit as x approaches negative infinity of 1 over x. And it doesn't matter whether I'm dividing 1 by very large positive numbers or very large negative numbers. That 1 or that piece of pizza is still going, that entire pizza is still going to get smaller and smaller and smaller as far as the area of each slice when you divide. So again, it doesn't matter whether we divide by positive or negative numbers. We're going to be approaching 0 either way. So both of these limits at infinity are equal to 0, which brings up another concept, horizontal asymptotes. Okay, so I'm going to graph this. We're going to use our calculators, and we're going to see what's going on with this function as the x values are increasing and as the x values are decreasing. Okay, so I've entered this function into our TI-84, and I'm going to hit the graph button. And we can see right away that as I move in the positive x direction, we are approaching y equals 0. And as I move in the negative x direction, we're also approaching y equals 0. So there is this horizontal asymptote at y equals 0. So HA for horizontal asymptote at y equals 0. So if we try to apply this, or we try to look at the relationship with this horizontal asymptote and our limits at infinity, if one of my limits at infinity approaches a real number, so in this case my limits at infinity are approaching 0, then there's also going to be a horizontal asymptote at that number. Okay, and we'll talk about it later, but I could have a function where the limits at infinity are different, and that just means each one of those numbers would be its own horizontal asymptote. All right, let's go back and look at our second example. So here we have a function, we're still looking at the two limits at infinity, but you'll notice that the exponents in the numerator and denominator are different, specifically the exponents on the leading terms. So again, it's not clear what the end behavior may look like, just given this what seems like a complicated function, but let's see if I can figure this out by rewriting it and simplifying it a little bit. So like I said before, when we are substituting in very large numbers, the only terms we care about are the first ones for both the numerator and the denominator. So this function, approximately equal to negative 3x to the 5th divided by 4x to the 5th when x is very large. And then, of course, we could simplify this to negative 3 over 4. Okay, which means this right here is much easier to take the limit of than our original function in black. But they will have the same limit. So this limit is equal to the limit as x approaches infinity of negative 3/4. And if we think back to our properties of constant functions, it doesn't matter what the x value is, right? Because there's no place to substitute in for x. So the limit of the function is always going to be the value of the function, regardless of what x is. So our limit is negative 3/4, which means our limit up here is negative 3/4. All right, let's look at the limit as x approaches negative infinity. I'm not going to do all the work down here again, because it's going to be the same. but I will rewrite the limit. So the limit of the black function is equal to the limit as x approaches negative infinity of negative 3/4, right? Because we just showed that we can, negative 3/4 is approximately equal to what the black function is when x is very, very large. So they're kind of the same function when x is very, very large. They're much different functions when x is not very large, right? They perform differently, closer to they perform very differently when the x values are closer to 0 than when the x values are much farther away from 0. Anyway, this limit's going to be the same because it's a constant function, which means the limit up here is also going to be negative 3/4. Maybe you've caught on to something from what you've learned in pre-calculus. Maybe you've been paying attention to these powers in the numerator and denominator, and you notice that in our first example, they were different. The denominator had a greater power than the numerator. In this case, the powers are the same. Now, we'll talk about the rules later, but again, this is going to lead back into something you've already learned from a pre-calculus class. Before we go ahead to our next example, let's see if we also get horizontal asymptotes. Well, we're going to get one horizontal asymptote at y equals negative 3/4, because in our first example, the answer to our limits was 0, and that was where our horizontal asymptote was. And in this example, the answer to our limits is negative 3/4, and let's see if we get a horizontal asymptote there as well. All right, so I've entered the function in our TI-84. I'm going to hit the graph button. And while it isn't, we don't have actual numbers on our axes because the calculator doesn't do that, we are able to see that there seems to be a horizontal asymptote at y equals negative 3/4. So again, the answer to our limits at infinity ended up being a horizontal asymptote of the function, both in examples 1 and example 2. All right, let's move on to our third example. Okay, this time we have what looks to be a less complicated function. There's only one term in the numerator, but we're going to treat this the same way. We are going to try to simplify it and get an approximate function that's easier to work with. So this pink function is going to be approximately equal to this blue function. We just take the leading term of the numerator, the leading term of the denominator, right? When our x values are very, very large. When x is very large. And of course, this is true when x is very large in the positive direction as well as when x is very large in the negative direction. And then, of course, if we continue to simplify, we get 5x over 1, or just 5x. Much easier to find the limit of. So the limit as x approaches infinity of 5x, well, if I just keep substituting in larger and larger positive numbers for x, my y is just going to approach infinity. This right here, this function is a polynomial, and we talked about the rules for polynomials in our first video of this lesson. So this limit is equal to positive infinity. Likewise, this limit's equal to positive infinity. Let's erase this box. We don't need that one. Same thing down below. We can simplify this function to 5x, which means we can take the limit as x approaches negative infinity of 5x, and that's going to be the same as this limit up here. Now, as we substitute in larger and larger negative numbers for x into the expression 5x, our y values are going to approach negative infinity, not positive infinity. So our limit as x approaches negative infinity is negative infinity. This example is a bit different because our limits didn't turn out to be real numbers. They turned out to be equal to infinity, which is not a real number. Again, it's just an idea. It means our function is either increasing or decreasing without bound. So let's graph these. Let's graph this function and see if we have any horizontal asymptotes. Okay, so I've graphed our function on our TI-84. I'm going to hit the graph button. And turns out our function does not have any horizontal asymptotes. So this looks a bit different than the functions we worked with in our first two examples. If you want to, you can zoom out a bit. Okay, but it's still going to look the same. All right, so I graphed or I entered our function into y1 in our calculator. I'm going to hit the graph button. Let's do zoom standard. We can see that a bit better. And we can see that our function does not have any horizontal asymptotes. So when the answer to a limit at infinity is infinity or negative infinity, that means that there won't be any horizontal asymptotes for your function. Okay, and as we go back to our functions, maybe you've picked up on that because you noticed that the exponent in the numerator was larger than the exponent in the denominator, or the power of the numerator was greater than the power in the denominator. And we've probably learned rules from that in pre-calculus, but we're going to talk through them again today. We're actually going to summarize those rules on the next page. And then we'll be done with video 2. So the rules for limits at infinity with rational functions. If the degree of the numerator is blank than the degree of the denominator, then the limit at positive or negative infinity will be positive or negative infinity depending on the sign of the a coefficient in the numerator, or the sign of the leading coefficient in the numerator. And we just talked about this. The degree of the numerator was greater than the degree of the denominator in our last example. And that's when your limits at infinity will be equal to positive or negative infinity. Case number 2. If the degree of the numerator is blank to the degree of the denominator, then the limit at positive or negative infinity will be the blank of the leading coefficients. So if the degree of the numerator is equal to the degree of the denominator, this was case number 2, then the limit at positive or negative infinity will be the ratio of the leading coefficients. So if you look back, if you want to pause the video, you can look back at example 2. The leading coefficient in the numerator was, I believe, -3. And the leading coefficient in the denominator was 4. So that's where that -3/4 came from. And case number 3, if the degree of the numerator is less than the degree of the denominator, then the limit at positive or negative infinity will be 0. For these last two cases, this is where the functions also have horizontal asymptotes at those values. So function will have horizontal asymptotes at those values as well. So the values of the limits. Okay, this is going to complete part 2. When we come back for part 3, we'll do some practice problems as well as talk about the calculus justification for where a function has horizontal asymptotes. Look forward to seeing you then. This is Mr. Fawcett. Enjoy the rest of your day.